everyone. My name is Alifia Ratna Rosanti.
Hello everyone, my name is Putri Anggun Fadila.
And I'm Siti Ayu Savitri.
We are the BHM Research Group from the Department of Chemistry, Islamic State University of WALISONGO, Semarang.
Ooh, textile dye pollution is happening. How can we actually reduce it? Maybe we should look for an effective wastewater treatment method. Hey guys.
Oh hi!
Hi. Look at this news. A river was contaminated because of textile dye wastewater. That's really alarming. By the way, I just got a Kinetics.
Yes, you're welcome. Oh, thank you so much. It's delicious.
Yes. Not only the food plastic is used.
So, what happened to the seeds?
They are usually discarded. In general, large amount of curry gases become agricultural waste every month.
Wait, what if this waste seed could be converted into activated carbon to remove textile dye from wastewater? What do you think?
The instruments used in this study are as follows. The carica seeds were washed with distilled water. Next, the seeds were sun-dried for 24 hours and oven-dried at 65 Celsius for 7 hours. The dry seeds were carbonized at 300 Celsius for 1 hour. The carbon was chemically activated using 15% sulfuric acid at a carbon to solution ratio of 1:5, in which 50 grams of carbon was mixed with 250 ml of 15% sulfuric acid solution. The mixture was continuously stirred for 24 hours. After activation, the sample were washed with distilled water until neutral pH and oven dried at 110 Celsius for 3 hours. CTAB solution 1% was prepared by dissolving 1 gram of CTAB in 100 ml of distilled water. Grams of activated carbon were mixed with the CTAB solution and stirred for 24 hours. The suspension was filtered and dried at 75 Celsius for 6 hours. Carbon and activated carbon was characterized by proximate analysis, moisture, S content, polarimeter, and fixed carbon. The AC and ACCTAB were analyzed using the BET method, PHPGC, IFTIR, and SEM-EDX. Batch absorption experiments were carried out using 25 ml of AO7 solution and 0.2 gram of adsorbent. The effect of solution pH, contact time, and initial dye concentration were investigated. After adsorption, the suspension was centrifuged and the residual AO7 concentration was determined using a UV-vis spectrophotometer.
The proximate analysis ratio represented in Table 1, compared with the carbonated sample, sulfuric acid activation reduced moisture and volatilometer while increasing phased carbon content, indicating effective removal of non-carbon components. The ions content remained below the Indonesian national standard maximum limit, confirming adequate for accessibility despite inorganic residues. Overall, the proximate analysis confirmed the sulfuric acid activation improved the physicochemical properties, making the activated carbon suitable for adsorption application. The beta surface area results are presented in Table 2. Sulfuric acid activation increased the specific surface area from 0.78 to 0.510 square meters per gram, indicating that chemical activation promoted pore development. Sulfuric acid acts as the hue-mediating agent, facilitating the composition of lignocellulosic component and removal of non-carbon substance, thereby creating additional pores. Nevertheless, the obtained surface area remained lower than many famous-derived activated carbon reported previously. This is attributed to the low carbonization temperature of 300 degrees Celsius, which was insufficient for extensive decomposition. Residual volatile component may remain within the carbon matrix, partially blocking pore formation. Despite this limitation, sulfuric acid activation still improved the pore structure compared with the FTIR spectra of carbon. Sulfuric acid activated carbon and ZAB modified activated carbon showed similar spectral patterns because they were derived from the same chemical pubescent seed precursor. However, several changes in the absorption band were observed after sulfuric acid activation and ZAB modification, indicating alteration in the surface chemical characteristics. Following sulfuric acid activation, the absorption band at approximately 1740 wave number, assigned to the J double bond OH stretching vibration disappears. In addition, selective were observed from 1597 to 1588 wave numbers, corresponding to aromatic J double bond J, from 1457 to 1442 wave numbers, corresponding to aliphatic JH or aromatic ring, and from 1156 to 1153 wave numbers, corresponding to JO stretching vibration respectively. These changes indicated sulfuric acid activation altered the surface functional group through dehydration and structural rearrangement of the carbon matrix. More pronounced changes were observed after ZAB modification. New absorption bond appeared approximately 2923 and 2855 wave numbers, corresponding to the asymmetric and symmetric stretching vibration of the methylene group from the long alkyl chain of ZAB. Furthermore, a characteristic absorption bond at 574 wave numbers, attributed to the JBR bond, was detected only to ZAB modified sample, indicating the presence of residual ZAB species on the activated carbon surface after the modification process. The surface morphology and elemental composition of adsorbent were characterized using SEM-IDX. The ACE sample exhibited a rough and irregular surface with numerous cavities and pores. After ZAB modification, the surface morphology changed noticeably, becoming more homogeneous and smoother with fewer visible cavities. These morphological changes indicate that ZAB modification altered the surface characteristic of the activated carbon. The elemental composition of ACE and ACE-ZAB was determined by IDX analysis. In addition, bromine was detected at 0.20% in the ACE-ZAB sample, confirming the successful incorporation of ZAB onto the activated carbon surface. The presence of Br is consistent with the chemical structure of ZAB, in which bromine serves as a counter ion of the surfactant. This finding is in agreement with the FTI result, which reveals the characteristic JBR absorption bond in the ZAB modified activated carbon. The simultaneous detection of the JBR functional group by FTIR and Br by ADX indicates that bromide containing ZAB species remained associated with the activated carbon surface after the modification process.
To understand the surface properties of the adsorbent, the point of zero charge or pH-PCC was determined. The pH-PCC value of the activated carbon was 3, indicating that the adsorbent surface is positively charged at pH value below 3 and negatively charged above this value. After ZAB modification, the pH-PCC increased to 6, demonstrating a significant change in surface characteristic. This increase is attributed to the introduction of positively charged quaternary ammonium groups from ZAB onto the carbon surface. As a result, the modified adsorbent maintained a positive surface charge over a wider pH range, enhancing electrostatic attraction toward anionic dye molecules. Therefore, ZAB modification successfully improved the surface properties and expanded the adsorption capability of activated carbon. The adsorption performance of both adsorbent was strongly influenced by solution pH. The unmodified activated carbon showed the highest adsorption capacity at pH 2, corresponding to its pH-PCC value of 3. As the pH increased, the adsorption capacity decreased due to the development of negative surface charges, which caused electrostatic repulsion with the anionic dye. In contrast, the ZAB modified activated carbon achieved its maximum adsorption capacity at pH 5 and maintained relatively stable absorption performance from pH 2 to 7. This result indicates that CTAB modification successfully broadened the effective pH range for acid orange 7 absorption. The effect of contact time on the absorption performance was investigated to determine the optimum absorption. Both absorbents exhibited rapid absorption during the initial stage due to the abundance of available active sites. The absorption capacity increased significantly during the first 30 minutes, followed by a slower increase as the active sites gradually become occupied and the system approached equilibrium. Because the increase in absorption capacity after 30 minutes was relatively small, 30 minutes was selected as the optimum contact time, providing efficient absorption while minimizing treatment duration.
Next, we investigated the effect of the initial acid orange 7 concentration on the adsorption performance. As the dye concentration increased from 25 to 200 mg per liter, the adsorption capacity of both adsorbent also increased. This is because a higher dye concentration provides a stronger driving force for mass transfer, allowing more dye molecules to interact with the available adsorption sites. At an initial concentration of 200 mg per liter, the CTAB modified active carbon achieves a higher adsorption capacity of 20.50 mg per gram, compared 18.99 mg per gram for the unmodified active carbon. These results demonstrate that CTAB modification is particularly beneficial for treating wastewater containing higher dye concentration. To better understand the absorption mechanism, the experimental data were analyzed using the pseudo-first order and pseudo-second order kinetics models. The results show that both adsorbents were best described by the pseudo-second order model, with R-squared values of 0.9998 and 0.9999 for the unmodified and CTAB modified active carbon respectively. These values were considerably higher than those obtained from the pseudo-first order model, indicating that the absorption process is mainly governed by the interaction between the active sites on the adsorbent surface and the acid orange 7 molecules. In addition, the second order rate constant increased from 0.1055 to 0.2411 gram per milligram per minute after CTAB modification, indicating that the modified adsorbent reached adsorption equilibrium more rapidly than the unmodified carbon. The adsorption equilibrium was further evaluated using the Langmuir and Freundlich isotherm models. For the unmodified activated carbon, the Freundlich model saw an R-squared value of 0.926 compared with 0.865 for the Langmuir model. Similarly, for the CTAB modified active carbon, the Freundlich model achieved an R-squared value of 0.734, whereas the Langmuir model saw only 0.129. These findings indicated that the activated carbon possesses adsorption sites with different energy levels, making the Freundlich model more suitable for describing the adsorption behavior of acid orange 7. Overall, CTAB modification successfully altered the surface properties of the active carbon, extended the effective pH range for acid orange 7 adsorption from pH 3 to pH 6, and improved the maximum adsorption capacity from 18.99 to 20.50 mg per gram. Although residual bromides ion caused partial pore blockage, the modified active carbon still demonstrated strong potential as an environmentally friendly adsorbent for the treatment of anionic dye containing textile wastewater.